All right, hello. So welcome to my talk about the surprising complexity of formatting ranges. I want to start by introducing myself. I'm a C++ developer at Jump Trading. I've been there for a little over 8 years. We're a research and technology-driven trading firm. It's a very cool place to be. We do a lot of very interesting problems. Outside of Jump, I've been a member of the C++ Standards Committee since 2016. I've been pretty active. I've written a lot of proposals on a wide variety of topics that have made their way into C++ 20 and now C++ 23. Kind of the biggest one lately is deducing this, but also a bunch of context for ranges papers, some comparison stuff. I have a blog that I don't post very often to, but I am very active on StackOverflow, where you've probably seen some of my answers. I'm also on Twitter. Outside of the C++ world, I'm a very big swim fan. To the point where I actually write for SwimSwam, which is the premier swimming media organization. And I also do work for the DC Trident, which is a professional swim team, which includes a couple of Tokyo Olympic gold medalists, Zach Apple and Anna Hopkin. All right, so formatting. In the beginning, we have to start with printf. And so the way that printf works is we have a format string with some number of placeholders, and then we take some arguments where the whole point is that the placeholders teach the library how to format those arguments. So in particular, the statement would print that the price of beef is $12.34. And this works by each placeholder in turn telling the library how to format each particular argument. So these are totally independent things. And as I change what one of the placeholders uses as a specifier, it changes what the formatting is of that argument, but only that argument. These are totally independent. And ultimately, this is based on, there's a specification mini language, which is the grammar is up there, although I don't expect anyone to remember it, and I find myself frequently looking it up. But printf is pretty error prone, right? Because we don't use these specifiers just to teach the library how to format our arguments, but also what types they have. And if you get that wrong, kind of all bets are off. But ultimately, the real problem with printf is that it's non-extensible. If I had a type like point, there's nothing I can do to teach printf how to format my type properly. It's just not possible. So then C++ introduced IOStreams. Which is a very different look and feel of a library than printf was. Because now, instead of having one format string, we have a bunch of pieces that we're streaming one at a time. So this code right here just prints my two ints as ints. But if I really wanted to format the first int as hex like I had before, we also have this suite of manipulators. And so I would stream std hex in the same way that I stream every other piece in here. And that will change the formatting of this int to be hex. But you'll notice that it also changes the formatting of the next int to be hex as well. These things are sticky. And so if I go ahead and add a whole bunch more manipulators, basically everything in the library that might be remotely relevant, you'll see that that affects the first parameter and changes the way it's formatted. And it also changes the second one as well, but in a slightly different way, right? The first one is 8 bytes wide, which is what I asked for with the setW, but the second one is only 5 bytes wide. And this is because some of the manipulators are sticky, in fact, most of them, but some of them aren't, like setW. And you just kind of have to know which is which. So ultimately, in IOStreams, we have this fixed set of manipulators, which is mostly sticky and as a result error-prone because you have to be very careful about resetting state. But importantly, it's extensible to user-defined types. So my point example from earlier, it's very easy for me to just add a stream operator, and now whatever types I want to use are printable just the same way as every other type, which is fantastic. This is a huge improvement over printf. Although I should add a footnote, it's not quite a fixed set of manipulators, even though most people kind of think of it as such. If you look at the CPP reference page for iOS base, and you scroll down a bit, you'll notice that there's this section called internal extensible array. And this actually gives you the ability to add arbitrary state to a stream, kind of whatever you want. So really, if you wanted to, you can write your own manipulators that are just as buggy and error prone as the standard library ones. And then there was format. So format looks a lot like printf. We have the same kind of format string with some kind of placeholders. The syntax for the placeholders themselves is different. We use braces instead of %, and then arguments. And it is those placeholders which teach the library how to format those arguments, right? And so in the same way, x is the specifier for hex, and that teaches the first argument to be formatted in hex. And the second one, by default, we just get the nice ASCII printed integer. And as I change the specifier for the first argument, it's only that argument that changes. Everything else stays the same. These things are independent from each other. Now, what format adds that printf doesn't is that we can also add numbers here. We don't just have to format all the arguments in order, we can identify specifically which arguments we want in each placeholder. Now, in this example, I'm just numbering them in the same order, so maybe that's not super useful, but I can just flip them. And more interestingly, I can format the same argument multiple times, which is different specifiers each time. So in terms of the grammar, the stuff within braces is called a replacement field. Pretty straightforward name, because it's something that's going to be replaced. If your replacement field contains a colon, then the part of that after the colon is referred to as a format spec. A replacement field need not have a format spec, or it could have one that's empty. The stuff in front of the colon is called an arg-id, which again need not be present. And so in this case, both of these arg-ids refer to the same argument, but they could refer to different arguments. The way you opt into formatting is you specify this class called formatter. Typically, it takes two template parameters, the type that you're formatting and a character type, since the format library supports arbitrary character types. But for the purposes of this talk, I'm going to pretend that char is the only character type and just ignore that for these purposes, just for simplicity. There are two member functions here. Parse, which takes a format spec and stores whatever state is necessary in the formatter object to be for future use by format. Note that this function is mutable, so that you can store whatever you need. And a format function, which is const, which now takes an instance of your type and can use whatever state that you've stored from parse to actually emit the representation. So let's talk about parsing. The context that you get is going to be a specialization of this type. But again, I'm just going to pretend that there's only one character type. So it looks like this. We'll have exactly this type. And you can see that this is basically a string view. We have a range that has begin and end that gives you specifically string view iterators. And you have these functions down here which do the argument ID manipulation. And we'll go through examples of how this actually works. And I want you to keep in mind also that format strings themselves can be arbitrarily complicated. So here's an example. For instance, I have this format string with a whole bunch of characters. The asterisk here is a fill character. Then the caret is our alignment. Caret means that it's center aligned. And then I'm using braces, which means that my width is coming from another argument. So rather than being baked into the format string as literal, it's another argument that I'm passing that could be a runtime variable. So what this does is it's going to print hi in a 10-character wide field, centered, padded with asterisks. And of course, we can manually number these things instead of using the automatic indexing. And also note that these format strings can contain arbitrary characters. So using chrono, for instance, the way that the format strings work is you just provide how you want your time point to be formatted, which is called a chronospec. And this example right here will print the year, the month, the date, the hour, and the minute. And so this is the time that I was constructing this slide. And so as you can see from these examples, there's no one particular character that can't appear, right? I can use colons, I can use braces, close braces, whatever. Anything basically goes. It's just up to the type to define what is valid for itself. So if we take a look at our original example and kind of zoom in on what the format string looks like, what actually do you get for your parse context? So in the first replacement field, we do have a format spec. It starts with just the X over there. And if we have one, the context will always start with at least that character. But where it ends is kind of loosely defined. And it might be different depending on how it's called. But it'll either be just the format spec in its entirety, in this case not including the close brace. It could include the close brace, or, and this is actually the typical case, it will go all the way through the end of the format string. And this is because the library knows where this thing starts. It understands the colon, and then knows that after that's your format spec, but it has no idea in general where this thing ends, because the format spec can include anything. So it has to rely on the parse function itself to know when to stop. So it gives you everything, and it's up to you to tell it when to stop. Similarly, if there's no format spec, as in the second example here, the library recognizes that there is none, so it might give you an empty context, and this is going to be the typical case. Or again, it could give you just the close brace or all the way through the end. And so the simplest thing you can do with parse is just return context.begin. This is a way of requiring that you have no format spec, because the contract on parse is to either return context.end or return an iterator that points to the close brace that is the end of that particular replacement field. And so if we return begin, that requires that, since either it's empty, and so begin will be end, or if the user tries to provide something, you're going to return an iterator to whatever their first character is, which won't be a close brace, which then the library will reject. So this is the simplest thing you can do. Note, return context.begin, not context.end, which will implicitly consume the whole format string, and then just weird things will happen. But this is kind of boring, right? Like, okay, the default formatting is good enough for a lot of contexts, and I imagine that this will be the most common implementation of parse. But let's say in my point example, what I want to do is actually maybe I want to format it either Cartesian or polar, and have that depend on a format specifier. So what I can do is I can add an enum to my state that parse is going to populate. So by default, it's Cartesian, but then what I'm going to go do is I'm going to see if they provide me a character. I'm going to read that character and use it to determine how I want to do this formatting. So I start by grabbing an iterator to context.begin. And so if I have no format spec, so either the iterator is already context.end or it's referring to a close brace, then I'm done. I just stop right there. Otherwise, I need to read the next character. And when I do that, I switch on it. And if it's C or R, then I'm going to store Cartesian. If it's P, I'm going to store polar. And otherwise, I'm going to throw an exception because this is not something that I support. And note that by throwing an exception, this no longer becomes a constant expression. And so in contexts where you provide this as a literal, we'll get a compile error, which is pretty nice. So how do we use this to format? Similarly to the format parse context, we also just have a format context, which again, I'll drop the character type. And I'll also drop the locale because let's just not get into that. The interesting thing about the format context is we still have this template parameter, right? It's templated on this iterator type called out. And all we know about this is that it's an arbitrary output iterator for char. And this becomes important later. Now, this could be a very nice iterator, like just char pointer, or it could be a back inserter to a vector of char, or it could be some very esoteric thing that's sending one byte at a time over the network. You don't know, right? And you have to handle whatever the user provides for you. And it has this arg function that gives you a dynamic argument, and we'll kind of look through examples of what that does. The simplest possible example that I could think of is, let's say I have a type that just has a single member char, and I don't want to support any format spec at all, so parse returns context.begin. And so all that format has to do is output that one single char. And the easiest way to do that is I grab my output iterator, and I just write that character directly into it, and I increment the iterator and return it. But typically, you're not going to deal with such low-level iterator manipulation, and you can rely on the format library to do something more higher level. So for our point example, the way that I'd write formatting, at least for Cartesian, is I'd use format2, which starts by taking an output iterator and then a format string and then arguments as before. So this kind of works. And then if I actually want to use the state that I have, I can just add an if statement. So if the type is Cartesian, I'm going to format it using x and y. Otherwise, I'm going to format it using r and theta, just calling my member functions on point. And so what that gives me is, by default, I'll get that my point is at 1, 2, since that's what the default implementation is. But I can pass in :p, and now suddenly I get r and theta. So by default, format prints a lot more decimal points on doubles than iStreams does, and you could do more work to trim that out. But we got this working, and that I think is pretty cool. But let's do something even more interesting, right? Let's talk about dynamic formatting. This is nice and all, but let's say I'm not actually willing to commit to deciding upfront at compile time that I want to format this in polar. And I kind of want to defer this a little bit later, so that maybe it's up to the user to provide this thing somehow as this extra argument, or maybe numbered somehow. Or maybe they want to pass in rectangular, right? How do I support that? So I can go through and I can extend my state with another kind of thing. So it's not just Cartesian or polar, but it could be dynamic. So I don't know yet at the time of parse what kind of state I want. And I'll additionally need to store an argument ID to be able to figure out, well, which argument am I actually going to load this choice from? So I need to go through and I need to extend the way that my parse works to start by handling an open brace, right? So if my spec starts in an open brace, that's going to refer to some kind of argument ID. And now I need to do something more complicated. So here, I know at this point I'm going to be dynamic. So now it's just a question of, is the user just going to provide open brace, close brace, which is going to be the automatic indexing, or are they actually going to provide a number for me? If they just provide open brace, close brace, I can just call next argument ID to store that, and I'm basically done. But if they want to provide a number, then I can use from chars, and I can check my error state, and I need to make sure that what they provided for me is actually a legitimate number, that they didn't stick in letters or arbitrary characters into there, and that from chars actually consumed the whole thing all the way to the close brace. And once I do that, I then can push all this stuff back into the parse API, right? So if we're doing automatic indexing, I need to call next argid to get the next argument ID that I need to store. If I'm doing manual indexing, I need to check to make sure that this number that the user gave me is actually legit. If I only have 2 arguments and they're trying to use argument ID 7, that's not a real thing, so this is going to fail. Also, the library is going to check for you that you're not mixing and matching. If you're using automatic indexing, you have to use automatic indexing for everything. If you're using manual indexing, you have to use manual indexing for everything. And so the library will verify that you do the right thing here. So now that we parsed all this stuff, we have our potentially dynamic type, and we have a potential argument ID. What do we actually do with it in terms of formatting? So to start with, we need to take our type and turn it into actually Cartesian or polar. If it wasn't dynamic to begin with, that's easy because it's already Cartesian or polar. But if it's not, at this point, we need to go and grab our argument ID. So this type is basically a variant, and we need to visit that variant. That API is a little bit cumbersome right now, but this is what it looks like. We'll kind of go into what kinds of things could be in that variant a little bit later. But basically, we only allow a char. So if the user provides a character, P or R or C, that's great, and we'll go and we'll do that parse logic and convert that into our enum as we had before. I didn't include that code. But if they don't provide a char, if they try to give me an int or something, that's something that this library can't handle, so it's going to throw an exception. Let's talk about generic formatting. So it's all well and good to format point, but what if I want to format optional? So the easiest thing I can do is, again, I'm not going to support any format spec at all, and I'm just going to pick the default thing. And a good default for me is just to do what Rust does. And what Rust does for optional formatting is that if it's engaged, you get sum, open paren, the value, close paren, and if it's disengaged, you get none. And this is nice, this is useful. But we might want to do something a lot more interesting, right? If I have an optional int, maybe I want to format it as hex. If I have an optional string, maybe I want it center aligned and padded with asterisks. You know, who knows? There's a lot more functionality that we might want to support. So let's see how we can do that. We start by adding a formatter for the underlying type. And we can change our parse to just completely defer to that. So this way, the specifiers that I support for optional T are exactly the specifiers that are supported for T. I don't have to do anything special here. But now, okay, so we're parsing our specifiers and we're storing that state, but we're not actually using them yet, right? This is just using whatever the default formatting behavior is for that underlying type. So first, let's split this off into 3 pieces. The 2 parts that are easy, which are the string literals, and then the actual underlying type. And we want to change this to be something else, right? In the same way that my only hook into parsing for the underlying type is underlying.parse, my only hook into formatting for the underlying type is underlying.format. And so that's going to take the value and some kind of context, really our context. And you have to remember to kind of do this dance. This is this interesting thing. So the whole formatting API is based on output iterators. You get an output iterator out of the context, you keep writing things into the output iterator, but the context doesn't necessarily know that this output iterator has changed. For some output iterator types, like back consider, this doesn't matter because those iterators don't have any state anyway. But if our iterator was something like a char pointer, the context kind of needs to know where that pointer has gone. And so in order for the underlying.format call to actually format into the right place, we need to teach the context that, oh, actually, we moved this thing. So this 2-step of doing context.advance2 followed by underlying.format is the way that we do that. All right, so with that intro out of the way, let's talk about formatting ranges. One of the issues with formatting ranges is that there's a lot of different possible formats for a range. Now, the simplest one and a pretty good default is we're just going to use square brackets, and we're going to delimit every element with comma space. It's a pretty good default. A lot of languages do this. There's no reason for us to do anything different. This works nicely for if we want to have nested ranges. Like if a range of a range, I just have more square brackets. This works just fine. But the interesting thing comes up when we have ranges of strings or chars. Since, well, we could just print them as is, but this becomes very difficult to read if those strings or characters are things like white space or comma, since it becomes difficult to find where one element ends and the next one begins. So a pretty good choice of default for these is to print them quoted. And in the case of things like newline, escaped. This makes it a lot easier to understand what the output is. But maybe you don't actually want to print the brackets. That's a typical thing too. Or maybe you want to print your range right aligned or center aligned or left aligned. Or maybe your range is something like a hash table and you want a representation for the format that makes that more clear, right? This isn't just a range of pairs. There's some meaningful relationship between these two types. So using something like braces with a colon is a more descriptive representation. Or maybe you have a set and so you want to use braces instead of square brackets to kind of differentiate from just a vector. And even if we reduced our space to just vector of char, well, we might want to print it quoted, because that's a pretty good default. Or we might not want to quote it. Or we might want to print them as integers, since in this case that's what we want. Or as hex with the base. Or maybe this is a MAC address, so I want to print it delimited with colons. Or really, I'm using a vector of char, but it actually represents a string, so I just want to print it that way, possibly unquoted. So the thing is, there isn't one correct answer for what the formatting for a vector of char should be. All of these are useful in one context or another. And so if the standard library is going to provide formatting for vector of char, it really had better support all of these, right? So the question is, how do we do this, right? A lot of these come down to what is the specifier that I want to provide for char? And that brings up our first problem, is how do we do a format spec for ranges? So the problem is, we just have some underlying type. We don't know anything about this underlying type. And in particular, we don't know anything about what its format spec is going to look like. All we can do is rely upon its parse to find me that close brace. And importantly, there could be other close braces there, right? We can't just look ahead and find one because we might find the wrong one. It's only the underlying type that can tell us when to stop. And so that kind of informs what the structure has to look like. In particular, the underlying type's format spec has to go at the end, because we have no other way of determining when it's going to end. And if we put it at the end, we can just use it to find what the real close brace is of our replacement field. And so that means that any top-level specifiers that I might want to provide have to go in front of that. And of course, after a colon, since everything starts with a colon. And so, for instance, I then might print this in hex with a base as an integer, or center aligned using n as my padding character in a 3-byte wide field. But I might also want to use n as my format spec as for the range itself. So n in this case means no brackets. And so how do I, as the library, differentiate between the n that's my top-level specifier and the n that's my pad character for my string filling? And the solution there is just add another colon. And the nice thing about this is this really just naturally stacks upon itself. So if I had a vector of chars, everything after the first colon is the specifier for the vector of char. Everything after the second colon is the specifier for each underlying vector of char. And everything after the last colon is the specifier for the underlying char for each thing. So in this case, I'm printing every char as hex with a base. And now I'm changing each underlying range of char to be center aligned 18 bytes wide using asterisk as the fill character. And the outer range doesn't have a bracket. And so these just naturally stack on top of each other, which works out pretty nicely. So how do we implement this? So to start with, we need a formatter for our underlying type. Unlike optional, where we could just use formatter of t, in this case, we need to do a little bit more type manipulation. And we need the type that we want is the range's reference type with the CV and reference qualifiers stripped off. So importantly, it's remove CV ref of the reference type. It's not the value type. This is a common issue that people run into, since most of the time, those types are actually the same, the value type and the reference type with all the qualifiers stripped. But the type that you deal with in ranges most often is the type that you get dereferencing the iterator. That's the reference type. The type that you get when you iterate over it with a range-based for loop, that's a reference type. And so for some types, like vector of bool reference, the value type is bool. And these things are different. And that conversion could be arbitrarily expensive. And there's no reason to pay for it. We don't need a value type here. The reference is the one we want. To start with, for parse, I'm just going to do the same thing I did for optional. I'm just going to pass through all the way to the underlying parse. We're kind of not going to deal with how to actually do the top level thing yet. And so let's go through format. We're going to surround our range with square brackets. So we're going to start with the open square bracket and the closed bracket. We need to loop over all the elements in our range. And And we're going to print every element in our range using underlying format, using that two-step that I showed earlier. We do context.advance to our iterator, and then we call underlying.format to format each element. And the last thing we have to do is conditionally print our delimiter between each character, but not before the first one and not after the last one. And so this is pretty nice, right? So if I have a vector of int, that can print just fine. If I have a vector of vector int, the logic I showed nests pretty naturally, so this just works. I can pass in specifiers that are different for each argument, and that works pretty fine too. I can use the range adapters, and that also works because it's just a range, and I don't really care what kind of range it is. And then I try to do filter, and it doesn't compile. So what's the problem? The problem is we took our range by reference to const, and then we passed that through into our loop. And filter, like a bunch of other range adapters, is not const iterable. The const version of that object just isn't a range, so I can't loop over it. Now, one thing we could do is we could pipe it into views all, which is going to take our filter and make a copy of it, and that copy is going to be mutable. And that kind of works. If the thing was a range that wasn't a view to begin with, this just wraps it in another layer of indirection, which isn't so bad. But if my view was neither const iterable nor copyable, like generator, which is kind of a very useful facility, this also won't compile anyway. So best case, I get extra overhead. Worst case, this still doesn't work. Not a great solution. Ultimately, the problem boils down to the way that we'd originally specified the format API in C++20 is that every entry point took a pack of references to const. And so there's nothing really I can do in my specialization for ranges. Well, like once it's const, it's const. I can't do anything with it. So during the course of working on this whole problem, Victor wrote this paper specifically to support types like generator that it would be nice to be able to format. And what that did is it went through and it changed the API to take everything by forwarding reference. And so what that means is if you pass in a mutable filter view or a mutable generator, that can be propagated all the way through to your format function, and now it's still a range, so you can actually iterate over it. So what we can do is I can change my function now to take a mutable reference. And so now this works. Except now I just lost support for printing const vectors. And that'd be pretty nice to be able to handle too, since those are ranges. So what I could do is, okay, I'll just add two overloads, one that takes an ref and one that takes an rconstref, and have them both defer to a function template. So that works. But if you think about it, like what's really the point of this function, right? If I have a range that's const iterable, like most of the ranges that we're familiar with, vector, string, all the containers, this function is totally pointless. It just adds completely unnecessary code bloat into our program, right? Because both of these instantiations work just fine. I don't need the second one. But if our type isn't const iterable, then this is the only function that matters, and the other one's totally useless. So it's not really a question of wanting to provide both, it's really wanting to provide exactly the right one of them. So what we do instead is we have this alias called format may be const. And what that does is it tries to just pick the right one. If R is a const formatable range, so R const is actually a range and I can format it, then I'm gonna pick R const because we wanna do the most const thing and that one works, so that's good enough. Otherwise, it has to be mutable, so it's the only option, and we can do that. And once we make that change, and we change the whole specification of the format library as a defect report 1 year after C++20 shipped, now suddenly filter works, and that's great. So let's talk about top-level specifiers. Let's say I want to support the end specifier. Like, I don't want brackets. The square brackets offend me. I don't want to print them. So we can add extra state to our formatter, and using that is pretty straightforward. Instead of unconditionally formatting the open and close square bracket, I just guard those with an if statement if that specifier wasn't provided. I'm not going to get into how to actually parse it since it's pretty straightforward, and this works. Cool. We've added more functionality to our range formatter. Let's go bigger. Let's say I want to support fill, align, and width for my range. So again, we're just going to add more state into our formatter. In this case, this is just some type that stores a fill character, some alignment, some width. I'm not going to get into those details. Now the question is, how do I format something aligned properly? So let's say I have the string hello, and I want to put it right aligned into a 7-byte wide buffer using a hyphen as the fill character. There's two basic strategies that you could use. You could just count the number of characters up front. It's like 5. Okay, I have 5 characters, and I know I need to write 7, so I can just write my 2 hyphens that I know I need, and then write the 5 characters that I have, and that works. A different strategy might be, I'm going to write all the 5 characters, and then I'm going to go through and insert all the hyphens that I need after the fact. So I'm going to count the characters as I go, and then insert the things that I need to insert. Okay, so which strategy should we use? The problem is that context.out, as I mentioned earlier, could be an arbitrary output iterator. In particular, it could be a write once iterator. So this whole idea of I'm gonna write some stuff and then I'm gonna go back and fix it up later, that's not an option. Second problem is I have no idea how many characters to write. It's just, I don't even know how to count. I don't know anything about this range type. I don't know anything about this underlying type. You know, it's not something like a string that string.size just tells me how many characters are in it. It's not something that like, it's an int, so I know everything about int, so I can just test format it and then see how many characters it took. In particular, I can't iterate the range twice to find out any of these answers. The range could be an input range, which means that I can only even iterate it once to begin with, so not an option to begin with. But even if the range wasn't an input range and I could iterate it twice, I might not want to, because iterating it could be arbitrarily expensive. There's just arbitrary code that needs to be run. I don't want to do it. And lastly, I need a format into context. So how do I even do this thing? It might seem like I've now gotten rid of both my possible strategies for doing this. But the key is like, we don't need to format into that specific context that we got passed in. We could format it into a different context. So let's kind of see like where we might go with this. Let's start by adding a new context. So I'm going to format into a vector of char. This is a type that I know a lot about. And I'm going to use back inserter into that vector of char as my output iterator. And so then I can change the body of my function to, instead of writing into the old context, to write into the new context. So the result of this loop is going to be I'm going to have some vector of char that's populated with all the contents of my range arbitrarily formatted however the user wanted. And at the very end, I transfer to the main context. So this is the only time I actually access the original context, is to get its output iterator to write into. But at this point, I have this buffer. I just have a vector of char, and I know how long it is. So if I want to write something right aligned, buff.size is how many characters I have. So now it's very easy to just write the characters I need when I need to do it to do alignment. And so this write padded align function is just a pretty straightforward problem to solve. So cool, ship it, right? So the first problem is, if we look at this, and we go and look at the specification for format context, is we never actually specified any constructors for it. This isn't something that the user is supposed to construct for themselves, so this idea that I'm going to construct one on my own with a new iterator isn't going to fly. But that's not a big problem, we can just add one. So then we have the second problem, which is much bigger, which is this underlying.format call into this context could do anything, right? It could do arbitrary formatting, and in particular, it could call this arg function, as I showed with the point earlier, to access some dynamic args of the context to do more custom formatting. And right now, we're not passing any into this context, so our new context doesn't have any arguments, so everything will just fail. So that's not great. We really do want to support everything. So that's fine. Let's additionally pass in our args into this new constructor that we're extending as we go to support our needs. But now we run into this problem that the type of the args is actually templated on the context. So let's kind of go into why that might be and explore what basic format args looks like. So this type is approximately, it's not exactly an alias for a span of basic format arg, but for the purposes of this talk, it's good enough. It has roughly that same API. Where basic format arg is a type that has this nested class handle and is otherwise a variant of a whole bunch of types. So it has bool, it has char, it has a bunch of different integral types, it has a bunch of floating point types, it has pointer to const char, it has string view, and it has this handle. So we can rewrite this a little bit differently and move the handle outside of the context and just pretend that basic format arg actually is that variant. And what this handle is for is this is what the library uses to format user-defined types. The handle is basically this type erased object that type erases this format call. And what this format function pointer does is it does the parsing and formatting in one go for a particular context. So when you do your format call, if it's intending to format some user-defined type, the library is going to type erase all the things it needs to do for that context since at the point of construction, it knows where you're going to format this thing, and that's what's stored into this handle. So if we want to construct our new arguments, what we need to do, basically, is we need to take this one variant from this one context and turn it into this variant using this other context, right? So how do we do that? Well, we can go through, and if our original type was monostate, that's very easy to convert to a monostate of the new type. And if it's bool, well, that's also pretty easy. And we can go down the list, and all of these are obviously trivial conversions because it's the same type in both variants. But if we had a handle of context originally, we can't construct a handle of the other context. We type erased for one thing. We don't know how to construct this thing for arbitrary other contexts. We can't just type erase every possible context in advance. Even if we could do that, that's a complete waste of time since most of the time you don't need it. So it kind of seems like we're stuck, right? How do we go from here? We can't just construct new arguments that we need. But here the key insight is that all the green ones here are actually plausibly usable, right? If I'm writing a format function and I need to use a dynamic argument, if that argument's a bool, I can go and get the bool by value, and I can make some decisions based on that bool. If it's a string view, I can get that string view. If it's an int, I can get that int, and I can make interesting decisions. But if I had a user-defined type, what I could plausibly get is this handle of context. And what am I supposed to do with it? I don't have any access to the original user-defined object. And in the context of format, I don't have a parse context that I can pass into the only thing I can do with this handle. So this thing is useless to me anyway. There isn't anything interesting I can do with it. So what we could do is just redirect that case to monostate. We don't actually lose any functionality here. There isn't anything you could do in general. So what we could do is we could provide an API called retargeted format context. And what this thing is going to do is it's going to do this basic format arg conversions for us. But only if necessary, right? We only have to go through this rigmarole if we actually have a different output iterator type. Because if we had the same output iterator type, these types would just match, and we could just use them directly. So for instance, if I'm using the formatter library, and I just happen to know that the main iterator type that format uses for all of its functions is appender of a memory buffer, and I implement my formatter this way, there's no conversion that's necessary, and this is now a cheap thing to do. And you can actually see an implementation of this on Compiler Explorer. It's possible to kind of hack up the library using things. But this works, and it's a viable solution. In fact, it's really the only way you could possibly implement this. So let's talk about another specifier, adding a delimiter, right? So comma space is a really useful default. That's probably what you want most of the time. But if what I want to do is format a MAC address, well, first of all, I want to format these things as hex, and I don't want brackets. We saw how to do that. But what I really want to do is I want to print it with a colon in between each thing, right? And not comma space. So what the format library provides is this facility called join. And what join does is it takes an arbitrary range and a delimiter, and what it does is it formats that range using that delimiter. And this just works. And it's useful. We use it in our code base a lot of time. But I'm kind of unsatisfied with the way this API ends up looking. And let me kind of go through why that is. So if I format a single MAC address, that ends up looking like this, and this works. If I have a range of MAC addresses, well, what I have to do is I need to take my range, and I need to transform them to be a range of these joins. But otherwise, this works. If I want to take my MAC address and center it somewhere, well, the way that the specifiers work for join is that they don't support fill pad align, so that has to be done separately. So I need to do this format call to get the string, and then I can pad and align the string. But this works. This is totally functional. But if we had a delimiter specifier, let's say we use D, and then we had some kind of dynamic argument to refer to another string view later that has a delimiter, like so, now these things look a lot closer together. And maybe we could even go one step further and allow a static delimiter. So the delimiter that I want to use for my range is actually part of the format string directly. One of the nice aspects of this is while the format strings are getting pretty complicated, and in particular, I'm using colon to mean wildly different things in the same format string, they're all layered the same way, right? I have my specifier for the underlying char, and then on top of that, I have my specifier for the range, and then on top of that, I have the specifier for the range of ranges, where if you looked at the original code, these things are all over the place. And so there's a kind of nice thing that we might gain from being able to put them in the same layers. And you can implement this, and I have an example on Compiler Explorer here that you could look up afterwards. And this is something that's still kind of an open problem of like whether even we want to do this at all. So let's talk about tuples, which is really the final boss of this whole problem. Let's say I want to provide a format spec for my pair of two ints, which is going to start with a colon, and based on our experience with ranges, we know that we need the underlying specifiers to go at the end. So for instance, I might provide two completely different specifiers for my two different ints, that's totally fine. But the problem is, how do we find this boundary between where the specifier for the first int ends and the specifier for the second int begins? Remembering again that specifiers could have arbitrary characters at all. How do I know when to stop? So one thing we could do is we can add more braces that the library imposes. And in particular, what this gains us is when we're parsing the first specifier for the time point, again, we have no idea where the time point specifier itself ends. Only the time points formatter knows this, and it knows that it's not this close brace, it's this close brace. But once it tells us this, well, we, the formatter for pair, know that, okay, well, what we expect now is the next character needs to be the open brace for the next element, and I know how to advance to the start of the next element specifier. And now that one can find me its close brace, and then I'm done. So this lets me find where these things actually start and end, and reminding that these things can, of course, be empty. So how do you implement this? Well, to start with, the same way that we've seen before, we need our formatters for all the underlying types. In this case, we have our formatter for a tuple is going to have a tuple of formatters. And we start the same way. If we don't actually have a format spec or it's empty, we're done. We don't have anything interesting to do. And so then we do a tuple for each, which is a very useful general function that probably belongs in everyone's toolkit. But it's just something that for every element of the tuple, it just unrolls a loop that calls the function for each element. And so what do we do for each element? Well, we know we're going to start and expect an open brace. And if we've run out of format spec or we don't have an open brace, that's bad. And then we parse that part. So we advance the underlying context so that the underlying type's formatter is starting from the correct spot and not from the very beginning where we were. And then we use the result of the underlying parse to know where we're going to end. And at this point, we expect that we've ended with a close brace, right? And if we don't end with a close brace or we've run out of the end, that's also bad. And so we're done. This is a nice kind of looped parsing, and now we support like arbitrary specifiers for tuples. And formatting looks very similar. Instead of tuple for each, we need tuple enumerate because now we actually need the index, because not only do we need to, because we basically need to loop over two tuples, the tuple object that we're actually formatting and the tuple of formatters that we need to use to do the formatting. And so this works. This is actually not too complicated to implement. You can find the implementation on Compiler Explorer. But this whole approach kind of has a problem. And I touched on this a little bit with the delimiter issue, where here's an example that we had with time point and the int. And if you notice here, we have this open brace, closed brace part of the format spec. And we have this in two different places. And here, it's a dynamic width. But here, it's a whole format spec for a different type, right? We have this part of the format spec that means these two wildly different things within the same format spec. So this is confusing, especially since people aren't going to format pairs and tuples very often, at least not with custom format specifiers. But stuff like dynamic width, that comes up a lot. So it's very likely that people are going to see this and not understand it. So let's kind of go back to the drawing board. We have this issue of we have these arbitrary sequences of chars that we don't know anything about that can contain any character. How do we know how to delimit these things? And so here, Tim Song had the bright idea that we could take a page out of what sed does. Because sed has this exact same problem. We need to do arbitrary string manipulation. We don't know anything about the strings. So what we do is we can just ask the user to provide a delimiter for us. In this case, well, none of my format strings has a pipe in it, so I can use pipe as a delimiter, or comma, or capital Y, like whatever I want to use is fine. But it's kind of up to the user to provide some unique character for this. But otherwise, this works. But how do we implement this, right? We have this issue where the contract for parse is that you parse until you either see a close brace or you see context.end. I can't really go through other people's parse functions and tell them to actually, for this case, I need you to stop at Y. And we don't really want to change the API to extend it for this case. So how do we do it? Well, we can't change the close brace part, but we can change the end part. And so what we can do is, we still have a tuple for each, but so we start by grabbing the delimiter, because that's going to be the first character. And we start by looking ahead for the next delimiter. Now before, we couldn't look ahead for the close brace because we didn't know if that would actually be the end, but in this case, we know the delimiter is the end. That's kind of the contract. So we look for it. If we don't actually find a delimiter, then that's bad. We stop. And then what we need to do is we need to change the context to set that to be the new end. Right? We stash the original end because we need to reset it later, and we temporarily set the current end to be this delimiter. And that way, when we call parse, it'll end where we want it to end. And at the end, we just restore it to the original end. And in particular, this part's kind of error-prone because we don't want to forget to restore it, so we can provide a simpler API. We call it, let's say, end sentry, that is just a scope-bound guard to temporarily change the end of this context to be this delimiter. And so this works, and you can implement it. But this of course has its own problems, which is, okay, well, what if I want to format a tuple of tuples? Now I need to pick two different delimiters. And the problem with picking a single character for a delimiter is that there's no clear visual bound for what that means. So when we used braces, these things surround something, so it has some kind of visual meaning, even if it is confusing. And so the end result is we don't really have a solution to this problem yet. What we're shipping for C++23, we're not going to support custom specifiers for tuple yet. As I've kind of shown, it's implementable either way. We can make either work. It's just a question of they're both bad for different reasons. So which one do we think is the least bad option? So looking forward to C++23. This whole talk came out of this paper that I started writing early last year called Formatting Ranges. And it has this kind of cute sentence in it where the original proposal said that the choice of formatting is implementation defined. Because at the time, I was mostly just frustrated by the fact that I can't even print a vector of int in C++20. And I didn't really care what it came out as long as, just print me the thing. It turns out that doesn't really fly. People aren't very happy with implementers just do whatever. So the final version of the paper is quite a bit longer and is slightly more detailed. I think even just the section on escaping strings is longer than the original draft was. But this is adopted for C++23, and so we'll finally be able to format ranges and tuples out of the box. It'll come with a utility for more convenient range formatting. So the join API that I showed earlier isn't part of this paper, but using range formatter, it's very easy to implement. So if you have ranges that you want to provide custom formatting for, this lets you do that pretty easily. It comes with a lot of specifiers for ranges and tuples, in particular fill align width for both. A no bracket operator has a way of formatting your range as a string or as a map, and the range formatter can allow you to provide arbitrary underlying specifiers. Strings and chars are going to be formatted as escaped by default for both ranges and tuples, and now you have an ability to, when you're formatting a specific string or char, to explicitly format that. But of course, there's a lot of future work that we still might want to look into. The utility that I described for doing fill align width for user-defined types, which I called retargeted format context, this is the only really way to do that kind of thing, but it isn't in the paper. We'll have to figure out what we want to do with that in a future revision. We will probably want to also add more support to actually parsing the format specs for this stuff, which I didn't show because it's actually fairly complicated. There's no delimiter specifier for ranges. So that's a question of do we even want to do this? How do we want to do it? And there's no element specifiers for tuple. If we want to do it with the user-provided delimiter way, we'll need to provide an API so that users can do this sort of thing, or come up with some other approach. And lastly, this paper and all this work would not exist at all without a few people. In particular, Viktor Zverevich, who is the creator of the format library, and who did a lot of work even updating format to keep it in line with this paper as this paper progressed over the last few years. Tim Song, who came up with a lot of the really clever ideas about how to solve these problems. And Peter Dimov, who's just a great library guy and is very useful to bounce ideas off. So I hope you enjoy all the stuff that you can do in C++23. Thank you. Yeah, questions?
About maybe a constant R. If it would be a forwarding reference, like adding a template to the function, would it be a solution?
Yeah, so you could write format to take a forwarding reference. That would work totally fine. The only problem is you get one more instantiation than you want, right? So, because if your range is something like vector of int, and you pass a mutable vector of int that you want to format, you don't want to have both a mutable vector of int and a const vector of int instantiation of that function. They do the same thing, they'll both work. It's completely unnecessary to have the mutable one. So doing it this way just reduces the amount of code that has to be generated.
So it seems that this solution might be relevant for other cases as well, not only for formatting. The ability to say, I want the const or non-const options. So why is it called FMT, maybe const, and not just STD, maybe const?
In this case, the specific thing that we're checking is that is tied into formatting. We're checking specifically that the range is formatable as a const range. So it's very tightly coupled into the library in particular. But this pattern comes up in general too. So this idea of just having something that looks something like std conditional t, something r const r is something that comes up a lot.
Thank you, and thank you for the talk.
Hey, that was great. Over the last iterations of the standard, there's been more of a move toward including like units with data types. So obviously, Chrono is a good instance of that. Is there some opportunity to, for instance, your MAC address example, if this was to say like alias a type or a vector or array of chars or whatever, that type itself might not be, like having the unit of that type might be sufficient to format as a MAC address, say.
So what I would do for MAC address specifically is I would just have a type that's MAC address. Like I wouldn't actually use like vector of uint 8. And I definitely wouldn't use vector. I'd use like an array of 6, unsigned char probably. But so I can have my type that's MAC address, and then I would just write a formatter for MAC address specifically. And so I would use that range formatter type that I mentioned, which means like I don't have to deal with the loop, I don't have to deal with the parsing the specifiers. And one of the things on that API is that it lets me explicitly pass in that delimiter that I want is like a colon. So that's useful. But generally speaking, like, yeah, it's just easy to write formatters. So you can just add your own for whatever like strong type that you want. So the chronotypes have formatters for all of them, and they print with units too, which is quite useful. So yeah, it's a good library.
Hey, thanks for the talk. So for formatting in general, we're kind of building these increasingly complex sublanguage, and this like talk really reveals just how increasingly complex it can get. And we're building it without any kind of static tools or way to provide static tools at the library level because, we don't have metaprogramming and these things aren't compile time. And what are your thoughts on the path forward to build up an ecosystem of static tools for checking these things? Should that happen in the language, or should it happen in linting tools? And if so, how do library authors get access to linting tools that have wide enough deployment to make this useful?
Yeah, so one of the things that actually format supports is that we can actually check at compile time that the format string is legit, that it actually matches. That it matches all the arguments that you provided, that the specifiers that you provided are valid for those types. This involves a fairly clever use of const eval. But if you're just doing like std print or std format, this is going to be checked at compile time for you. It's very cool. This is one of the format DRs that we added a year after C++20 shipped. Very useful. The problem is, while it won't compile, which is great, it's a lot better to not compile than compile some nonsense. You don't really get a great error out of it. So like what you'll get out of the format library, for instance, is what it does is it'll call a function that just isn't a context for function. And so the error that you'll get is like error called to non-context for function isn't a constant expression. And sometimes you'll get like a literal in that call, which is like useful. But there's only so much information that you could provide that way, right? Like what I really want to provide, like in my point example, is if you provided, let's say, W, as your specifier for point, like I want to give you a compile error that says that W is not a valid format specifier. Please use C, R, or P. And there's no way for me to do that right now. There's no way for me to provide a custom compiler error message. That is probably the biggest thing that we could benefit from in this case. Because then like it becomes so much more user-friendly. The other thing that would be much more useful is that one of the things that you can't really do right now is that, okay, I get this format string and it has to be a constant expression. It'd be very, very cool to be able to decompose it as a function argument into like its pieces. So there's going to be like a string literal piece and then like a replacement field that I want to do some pre-processing on, and then a string literal and then another replacement field or whatever. And you can't really do that while keeping the same shape of the API. So one of the things that the format library provides is it has this other compile time API. So if you wrap your string literal in this format compile macro, it'll do more stuff for you and it'll produce like a more efficient formatter. But like that's not like the direction that we want to go in. Like you're like, I just want to provide a format string. I don't want to have to wrap it in whatever nonsense. So that's like a great example where like if we had context for function parameters, for instance, I would want the format string to be a context for function parameter. And then I can keep the shape of the API the same. And at that point now, this is just like a constant. And I can do whatever cool stuff that I can do with constants, and I can do whatever arbitrary manipulation. And then if I can then also provide really nice diagnostics for the user, that's basically everything that we might want to do. Also, there's more interesting ways that we could do something like that. So right now, that kind of decomposition I mentioned, like you can write that today. It's fairly tedious because it's very hard to write like iterative compile time code while keeping constantness. It's like a different sub-language in a way. And so if you look at something like Zig, for instance, if you look at like Zig's implementation of printf, which you can implement in Zig very easily, it has this notion of like compile time variables that are local to the function that are mutable. And so like if you could build up this arbitrary state internally to the function, you could do that in a way that's like easier for people to write while preserving the power of it, which would also be, I think, super cool, like a very useful direction to go into. Yeah. All right, thank you.